Notes 10C. Dividing polynomials. Objective. I can divide polynomials of degree 1 and 2. Essential question. How do I divide a polynomial? Look at this vocabulary. We have f divided by g, we have greatest common factor, wholes, asymptotes, and synthetic division. So let's review factoring the greatest common factor. So we have 3x squared plus 6x. So let's go ahead and do the cake method to divide out the greatest common factor. First, we determine the greatest common factor of 3 and 6. That's 3. 3x squared divided by 3 is x squared. 6x divided by 3 is 2x. Next, you're going to ask yourself the question, do they both have an x? Yes. We take the smaller degree. 1 is smaller than 2, so we're going to take out one of those x's. X squared divided by x is x to the first power. 2x divided by x is 2. There's nothing else besides 1 that we could divide out, so that's it. Our greatest common factor is 3x, and our quotient is x plus 2. So at the top in the numerator, we're going to write 3x parentheses x plus 2. Let's do the same thing for the denominator. 3x squared plus 15x. First, we determine the greatest common factor of 3 and 15. It's 3. 3x squared divided by 3 is x squared. 15x divided by 3 is 5x. Then we ask ourselves, do they both have x's? Yes. The smallest degree is the first x to the first power. X squared divided by x is x to the first power, and 5x divided by x is 5. So nothing else we could take out. This is our GCF, 3x, and then we have our leftovers, x plus 5. So let's rewrite the denominator. 3x parentheses x plus 5. So we factored our GCFs. 3x divided by 3x gives you 1. So our simplified expression is x plus 2 at the top of the numerator, all divided by x plus 5 in the denominator. That's our simplified fraction. Let's look at this one, wholes and excluded values. So, from the previous example, we factored it out, and this gives you 1, the 3x divided by 3x. Now, since they simplify out, and they have a variable, that is what is called a whole. So that means we have a whole at x equals 0. Basically, we set what we canceled out equal to 0 to solve for x. So we have 1x equals 0. That's a whole. That means that the domain does not include 0. It's undefined there. There's another x value that's not included here, and we'll talk about those kind later in the video. Review reducing fractions. We have 60 divided by 75x. Well, 60 and 75 could both divide by 5. 60 divided by 5 is 12. And 75x divided by 5 is 15x. You can still simplify this more. 12 and 15 both divide by 3. 12 divided by 3 is 4. And 15x divided by 3 is 5x. So that is our simplified fraction, 4 over 5x. The next one, we have 0 divided by 12. Well, 0 divided by a number besides 0 is 0. And then we have 70x squared divided by 100x. You divide both of these by 10. So we have 7x squared over 10x. They also both have an x, so we could take one of those away. So we could divide each of these by 10x. If we have x squared and we took away one of those x's, we have x left. And then we have 10 in the denominator. So our simplified fraction is 7x over 10. Let's talk about the quotient property, subtracting exponents. So we have x to the fourth times x times y to the sixth power all over x cubed times y squared. Well, first we can expand these so you can get a visualization of what we're about to do. So after we expand it, we have 4 x's at the top and 6 y's at the top. At the bottom, we have 3 x's and 2 y's. So we're going to match these and cancel them out. X divided by x is 1, this is 1, this is 1, and then we'll do the same thing for the y's. And then we're going to count how many x's and y's we have at the end. So we have an x up here, and we have 1, 2, 3, 4 y's. So we have x, y to the fourth power. Now when these numbers get really large, it's kind of hard to expand them. So here's the other way you can do this. We can write x to the 4 minus 3, so we have the numerator's exponent minus the denominator's exponent times y to the 6 minus 2. Again, we subtract the exponents. And that'll give us the same answer, x, y to the fourth power. Next, we're going to talk about long division. Basically, you have an expression divided by another expression. We see how many times x goes into x squared. Be x times. It's just like regular division here. We divide, x squared divided by x, multiply x times x, which is x squared, to each term, subtract, and then you bring down. Repeat that process until you get to the end. Sometimes you'll have remainders here, and sometimes you will not. Here's another way you could do this. It's called synthetic division. So here's the same problem, but this time we're going to do it a different way. So we have x squared plus 3x plus 2 all over x plus 1. So what you want to do is set this equal to 0. If you set x plus 1 equal to 0, our 0 would be x equals negative 1. We put that in the box. Then we put a, b, and c right here. Because the coefficient of x squared is 1, the coefficient b is 3, and then c is 2. So we're going to bring down 1, and then 1 times negative 1 is a minus 1. 3 minus 1 is 2. 2 times negative 1 is negative 2. 2 minus 2 is 0. So our quotient is 1x squared plus 2 with a remainder of 0. So this is going to turn to our x column, and this is our constant column, and this is our remainders. Now let's go over vertical asymptotes. Basically, a vertical asymptote is a vertical line that a graph will never touch. Basically, it's when the denominator equals 0. Doesn't exist there. So on this one we have x squared plus 3 all over x minus 1. Your vertical asymptote would be at x equals 1. Because if you plug in 1 for x, you get 0, which is undefined. That's a vertical asymptote. Number 8, we have two vertical asymptotes. We'll set each of these binomials equal to 0. b minus 7, b would equal 7 here, and negative 5. So if we had 7 right here, we'd get 0. If we put negative 5 in for b right here, we'd get 0. And then the last one, 9v minus 4. We'll set this equal to 0. Solve for v. Add 4 to each expression. 9v equals 4. Divide each term by 9. So we get our vertical asymptote. V equals 4/9. The last examples we're going to go over are horizontal asymptotes. These are asymptotes you'll see most in this class this year. It's basically a horizontal line that a graph never touches. So to find these with an expression like this, we take the leading coefficient for each of these. If the degree on the numerator is larger than the denominator, then it does not have a horizontal asymptote. So we just put none here. When the degree in the denominator is larger than the numerator, you have a horizontal asymptote, specifically at y equals 0. Now the reason why is because we can really put 0 n to the second power over n to the second power. 0 over 1 equals 0. (63v minus 5 all over 9v minus 4). We're divide 63 divided by 9. That's 7. Y equals 7. And then the last one. It's another one where the denominator has a higher degree. So that's y equals 0.